Okay, so now that we've looked at a horizontal plane for uniform circular motion, we're going to look at swinging objects vertically. So like in front of you, or swinging a pail around with your arm, swinging your lanyard with keys, etc. So in uniform circular motion, it only involved one applied force because the motion was horizontal. When we start to rotate something in a vertical plane, there are now two forces acting. So we have the force of gravity and a tension force. Objects moving in a vertical plane create unique problems because the weight plays different roles at different points in the circle. So we use the directions as positive for forces acting towards the center of the circle and negative for forces acting away from the center of the circle. So at the top of a circle, we have a tension force that is towards the center of the circle, and we also have a gravitational force. So both of these are positive in this case. So together, we would add those two forces to get the net force. The net force in this case is the centripetal force. So overall, centripetal force is the force of gravity, which is positive, plus the tension force, which is also positive. So again, gravity's direction can be positive in one point of a circle and negative in another point of a circle. So at the bottom of a circle, we can see that the tension force is still acting towards the center of the circle, which is definitely not at this point, but whatever. However, the object being swung around the circle is here now. So the force of gravity is acting away from the center of the circle. So F net is the force of gravity and tension. However, this case, gravity is its usual negative self, and it all equals the centripetal force. So uniform circular motion requires a constant centripetal force. If it's a constant centripetal force and gravity isn't changing, the tension force is changing throughout. Now we know this because if you were swinging your lanyard around and it didn't quite have enough speed to go around the entire circle, it would be extended fully at the bottom of the circle. However, it would start to collapse in on itself at the top. So we can see that the tension forces are different in that case and apply it to when we get to a uniform circular motion. Okay, so all that to say, everything else is the same. In terms of calculating forces, we just need to consider where it is in each case. So in example 1 here, a 1.8 kilogram object is swung from the end of a 0.5 meter string in a vertical circle. If the time of revolution is 1.2 seconds, what is the tension in the string at the top of the circle and the bottom of the circle? So remember, centripetal force is constant throughout. So we can calculate the centripetal force for this entire problem, whether it's at the top or the bottom of the circle. So we had its mass, we have the radius, and the time of revolution is the period, which was 1.2 seconds. So we plug that all into our FC formula, which again we derive from using AC is equal to 4 pi squared R over T squared, and that FC is equal to mass times acceleration centripetal. So we calculate the centripetal force of 24.67 newtons. We can also calculate the force of gravity in this case. Again, in my practice, we need to consider it as a negative 9.81, so we will get a negative 17.66 newtons. Again, because gravity is always acting downwards. So now that we are in this case, we can use this information calculated for the top and bottom piece of our diagrams. At the top, both gravity and the tension force are pointing towards the center of our circle. Because of that, they're both going to be positive in this case. So FC is always F net, the overall force experienced in this circle. So FC equals FG plus FT. Now we know what FC is and we know what FG is. Again, it becomes the positive version in this case. So we can rearrange and find the tension force. We should have 2 significant digits here, so 7.0 newtons. Then at the bottom, our case is a little bit different. The tension force is acting towards the center of our circle. However, gravity is acting away, so it is a negative. Subbing these values in, we get 42.33 newtons, which should be 42 newtons. So we can see that the tension force is greater at the bottom of the circle than it is at the top of the circle. Okay. An object is swung in a vertical circle with a radius of 0.85 meters. What is the minimum speed of the object so that it remains in circular motion? So little information. What we know is that FC is equal to, FG and FT. Now, at the bottom of the circle, we have our largest tension force. But centripetal acceleration centripetal force is the same at the top and the bottom of our circle. So what we're going to solve for is at the top of the circle. At the top of the circle, we have to overcome the force of gravity that is pulling it towards the center or out of rotation. Tension force is what's keeping it in the circle in the first place. So if we say that the tension force is the lowest that it needs to be to keep it in the circle, that would be 0. Okay, anything over 0, this will continue to rotate. So the minimum speed we're going to say is when the tension force equals 0. Therefore, if tension force is gone, we are going to say that the centripetal force is equal to the force of gravity. We simply need to overcome the force of gravity pulling it down out of the circle, or rotation, I guess I should say. So when we equate these two, we can't even calculate anything because we don't have mass. So FC was equal to mv squared over r, and FG is always mg. So we put these equal to one another. Now, because FG is positive in this case, I actually just put mine in absolute values. So I have that V is equal to the square root of the absolute value of G times R. And I do that because G is a negative value and we should be putting it in as a negative. In the end, we're going to get this exact same answer though, because we have a radius of 0.85 meters, we get 2 significant digits. So rather than 2.89 meters per second, we should get 2.9 meters per second. I'll include a little bit of extra resources on this topic because I think that this one was really tricky. Just recognizing that the tension force could be 0, and that's how to solve this one. Go ahead and take a look at some of those practice problems. Again, it's really important that you're practicing on your own. And don't forget to do the formative quizzes online or the check-in quizzes online.